Thank you, and thank you for the chance to speak at ODSC East. So let me start by introducing ourselves. So we're from a company called Petuum, which was founded out of a team at Carnegie Mellon University doing research in machine learning and deep learning systems. So my name is Aurick. I'm the CEO at Petuum. So in the last couple of years that we've been around, we've worked on several different AI solutions for a spectrum of different clients ranging from manufacturing, logistics, healthcare, and education. More recently, though, we've started to build a composable platform for supporting MLOps, which is drawing from many of the lessons that we learned from several of these use cases. And it's this platform for MLOps we're working on that I want to talk to you about today. So let's get into it. So one of the most notable trends in AI and machine learning today is that applications are becoming increasingly more diverse and more complex. For example, at Petuum, we built a question answering system that by today's standards would be considered relatively simple. And even if we only consider the core AI logic in this Q&A system, it already exhibits a high degree of complexity across several different steps and sub-steps of processing. For example, pre-processing inputs from the user, finding relevant passages from a large corpus of text, ranking the passages on their relevance, aggregating answers from those passages, and then finally applying style transfer and bias reduction before arriving at the final result. And when we're finally ready to enter the MLOps stage of continuously maintaining, monitoring, and improving the application in production, we find that the core AI logic is just a very thin slice of the overall operational lifecycle. And we find ourselves bringing in new tools and frameworks to support bits and pieces of our MLOps needs, like data annotation, model retraining, model evaluation, and deployment and monitoring. And we end up with many different moving parts at multiple different layers of the stack, all of which need to work seamlessly from end to end to ensure a successful outcome for our application. And at the same time, there's an increasingly proliferous and fragmented ecosystem of tools supporting AI and machine learning. So this chart here shows just a part of that ecosystem, which already has hundreds of tools, each supporting a part of that an AI application's needs, from data annotation to the modeling techniques to the systems for deployment. And to build our question answering system, we took the bits and pieces that were best suited for our application and stitched them together by writing a bunch of custom glue code. But a different team working on a different AI application might see completely different needs and stitch together a different set of tools and frameworks than what we did. And yet another team might make a different set of choices than either of us altogether. So the proliferation of tooling and the custom glue code needed to stitch them together is what we believe to be the source of many common problems in MLOps today. For example, applications built this way are more likely to become difficult to maintain and upgrade, exhibit gaps in their end-to-end observability and automation, and cause ineffective use of team expertise, such as data scientists spending a lot of time struggling with infrastructure issues rather than focusing on the key data and modeling problems. And as a result, it becomes difficult to scale these applications when its number of end users increases, or as the size of the team maintaining it grows. And on the other hand, we believe that MLOps will eventually be a highly composable, automatic, and scalable practice, which is enabled by flexible composition with standardized interfaces. And this way, AI applications will be easily upgraded by swapping in and out reusable components, able to be observed and monitored at a glance from end to end, achieve comprehensive automation while still gracefully enabling humans in the loop where it really matters, and providing a framework for collaboration that lets members of the team specialize within well-defined boundaries. So to tackle some of these challenges, we've been working on a platform for MLOps that's based on full stack composability and extensibility. The goal is to enable users to flexibly compose and compose the diverse building blocks from the ML tooling ecosystem in standardized ways to create new AI applications. The core of our framework is based on 3 layers of composable abstractions. First, a standardized interface for data that acts as a contract between different people or software components. Second, a representation of multi-step pipelines that makes it easy to take machine learning code from the local development to cluster deployment. And lastly, a representation of long-running infrastructure that supports the entire operational lifecycle of AI applications with end-to-end observability. And the guiding philosophy behind these abstractions is to be opinionated about the interfaces between different building blocks while being unopinionated about what those building blocks can be. So in doing so, we enable extensible support for different data types and attributes, different code dependencies, and different long-running infrastructure services. And it also promotes a clean separation of concerns, enabling team members to specialize within their roles and specific execution systems to optimize different parts of the end-to-end application. And so, for example, we've been working on such an execution system called AdaptDL, which we actually plugged into our Composable platform to accelerate deep learning training for one of our major clients. So let's dig a bit deeper into each of the three layers of composability. First, data is often the object of interchange between many steps of an end-to-end machine learning pipeline. And each of these steps may be implemented using libraries that accept a slightly different data format. When there's no single standard data format, we're encouraged to write a lot of custom glue code between every pair of steps that need to pass data to each other. But doing this couples each step in the pipeline to the end-to-end task, which limits the reusability of each piece of code in the pipeline. On the other hand, if we're using a standard data format, it actually decouples each step of the pipeline from each other, making it easier to reuse each step in different pipelines or to recompose steps within the same pipeline. A second problem that arises is friction when collaborating within a team. As we saw earlier, modern AI applications can be composed of many different steps and sub-steps, which are often implemented by different members in a team to speed up development. But collaborating efficiently in this way requires the two people to agree on a common data format that acts like a contract between them and their pieces of code. So although there are existing solutions for data contracts that work well for structured data, we found that it's actually missing from the unstructured data world. And our solution for this problem is called the data pack, which is a standard format for expressing the markups, annotations, and attributes, as well as the raw data itself. For example, the annotated spans of text in an unstructured text document or the bounding boxes for objects in an image. And these attributes are classified according to a hierarchical ontology of customizable types. And for example, at Petuum, we also worked on a medical note highlighting application, which used an ontology consisting of a span that refers to any span of text in a document, an entity mention, which is a more specific instance of span referring to any named entity, and a medical entity mention, which is a domain-specific instance of entity mention referring to a medically relevant entity in a doctor's note. So similarly, the data pack can be customized by defining an ontology for other domain-specific applications. And the code that operates on an attribute within this ontology can operate on all of its descendants, which promotes modularity and reusability of code. And lastly, the ontology can be written down in a file and shared with the entire team, which acts as a fixed data contract that fosters better, more effective collaboration. So next, let's talk a bit about pipelines. One of the biggest challenges with machine learning pipelines is that their execution requirements can be extremely diverse. For example, an inference pipeline might be deployed as a network of long-running HTTP services that need to handle user queries in near real time, while a training or evaluation pipeline might need to be run periodically or on demand and need to support large-scale batch processing and distributed training. However, they often share large subsets of the same logic. And a problem that we see repeatedly come up is that to support the different execution objectives, this common logic gets rewritten many times for each setting. And doing so not only adds additional work, but also introduces risks that jeopardize the reproducibility of the pipeline between different execution settings. So to address this problem, we created an intermediate representation for pipelines that captures the core logic of each pipeline step. And the key idea here is to isolate the core machine learning logic from the execution level details so that code only needs to be written once. We then built a pipeline compiler that automatically transforms a pipeline written in Python code to artifacts that can be deployed on a diverse set of execution systems. For example, Argo or Airflow can be used for batch execution, or we can generate a network of Amazon Lambda functions to serve the pipeline with high availability in the cloud. And during pipeline compilation, we can also apply smart optimizations, such as reducing the latency of the pipeline by fusing different processors or increasing throughput by parallelizing certain processors. And one research direction that we're working towards that we're really excited about is applying hyperparameter tuning jointly to all processors in the pipeline in order to optimize for an end-to-end metric like prediction accuracy. And lastly, the intermediate representation also promotes a cleaner separation of concerns within a team. A data scientist can develop and test a pipeline using their favorite tools on a local workstation or cluster, while an MLOps engineer can take the automatically generated artifacts and configure them for deployment scenarios. Finally, we're also building a new composable abstraction for infrastructure, which allows users to easily compose long-running services that support the operational lifecycle of an AI application. So a very simple example is a simple lifecycle that might have 3 steps. For example, serving an inference pipeline to end users, collecting unlabeled data to be labeled, retraining the models on updated data, and then deploying the new models out to be served again. And our abstraction represents the infrastructure that supports this lifecycle as a graph consisting of components and flows. Components are long-running systems and services, while flows are intermediate storage used by components to interface with one another. And flows are also standardized and automatically provisioned by our platform. So some examples include endpoints for pub/sub messages, volumes for access to shared files and directories, and version repositories to track models. And each component can have inputs and output flows, and can also express their own user interfaces to gracefully support human-in-the-loop interactions, such as a graphical interface for labeling incoming data. And components are also highly extensible, meaning that we can incorporate almost any custom or third-party tool into the lifecycle. For example, stitching together TensorBoard to monitor the progress during training. And one advantage of using a graph representation is that it really simplifies the creation and maintenance of the infrastructure. For example, we can compose the entire graph using a graphical interface or edit and version it using configuration-based format. And the resulting graph can then be deployed on any Kubernetes cluster, whether it be running on AWS, Google Cloud, or on premises. It also enables at-a-glance observability of the entire application lifecycle, end-to-end manageability, configurability, and upgradability. I wish I could spend more time talking about the details of the system, but since I think it's something really unique that we're bringing to MLOps, but we still have a video demo coming up, so let's get to that. So before the video demo, I want to first mention that our platform is currently in very active development, so there will be some rough edges here and there. But hopefully it'll give everyone a more concrete idea of some of the things that we've been building. And without further ado, let me introduce Tong, our Director of Engineering at Petuum, who will walk us through the video.
Yes, thank you, Aurick. Let me share my screen first. All right. The goal of this demo is to show the great productivity gain enabled by the Petuum approach Aurick just described, covering local development, operationalization, and MLOps process automation. Our demo story starts with a data scientist. She is developing a language translator from English to Arabic in her local dev environment. The data scientist choose Petuum's pipeline API for this task. As you can see, the translator can be expressed as a pipeline of NLP tasks. Each NLP task is modular and can be reused to compose other NLP applications. Now, the translator is ready. The data scientists want to publish it as a service for more people to use and test it. The deployment task can be achieved simply with two simple steps. The first step is to insert one line of code into the pipeline definition program to enable serialization. The next step is for the data scientist to submit the code onto a Petuum Platform cluster for deployment. A noticeable command line argument is the execution mode. In this case, it is HTTP serving. Petuum Platform also support the batch execution mode without modifying the pipeline. Well, the submission process is ongoing. It's worth mentioning that what happens under the hood is that the pipeline logic is transferred into Petuum's unified pipeline representation, and the code is packaged. Once you have an application in the unified pipeline representation format, it can be targeted at a different environment for execution. In this case, the target is Petuum Platform's pipeline execution engine. Now, the submission process is completed. The deployment can be taken over by an MLOps engineer. Once a pipeline is submitted, it will show up as a project in the platform's UI. Clicking on the project will show the visualization of the pipeline. As you can see, the pipeline is visualized as a linear graph. Here, the graph nodes maps to the NLP task as defined in the original pipeline code. The pipeline starts with a reader. More importantly, it has the translation model in the middle. The edges connecting those graph nodes representing the data being transferred across the entire pipeline. The data on the edges is in Petuum's unified data format called DataPack. For the MLOps engineer to deploy the pipeline as a service, she may still need to further configure the pipeline. Firstly, we need the name for the endpoint. For any NLP task requiring more computing resource, we need to override the default configuration value. For example, we want to run the translation model on GPU instead of on CPU by default. We also want to specify the mount path of the model folder where the pipeline loads its model from. Once the entire pipeline is reconfigured, it's ready for deployment. The deployment task can be easily achieved with a simple click-through experience, as you will see next. Firstly, we need to create the service by specifying the required attributes like a workflow name. Once the service is created, you will have a URL assigned to the endpoint so that any client code can be used to invoke the entire pipeline. While waiting for the service to start, I would like to mention that given an application expressed in the Petuum Unified Pipeline Representation format, along with a target execution environment and the corresponding execution mode, Petuum Platform can perform adequate optimization to achieve better performance. For example, in the HTTP serving case, the platform tries to fuse the graph nodes to reduce the data transfer overhead along the edges, so to achieve low latency. Now the service is ready. The data scientist can send a simple request to the endpoint to try it out. In her test code, it contains a simple input in English. The test code logs has 3 parts. Firstly, the input in English. The second part contains a response in Arabic, which is the translated text. The log also has the version number indicating the version of the model used for the translation. Since the deployment of the translator, the team has been trying to improve it. They want to automate the process to retrain the model and use the new model to update the deployed pipeline. To enable the same pleasant user experience as shown before, we bring composability down to the infrastructure layer. Petuum Platform supports infrastructure as a graph with its unified pipeline representation. This is an example of an implementation to automate the model retraining and pipeline updating process, expressed as an infrastructure graph. In this example, we have the nodes. The nodes now representing reusable infrastructure components instead of NLP tasks as used by the data scientist to compose the language translator. The edges are called flows, representing the mechanism to transfer data between the nodes. In this example, we have 5 infrastructure components drag and dropped to the canvas from the component library in the lower pane. It starts with a data uploader, which exposes an endpoint for remote data uploading. It has 2 batch executors, with one executing the data preprocessing logic, the other executing the model retraining logic. We also have a generic service component exposing a browser-based file browser so that user can inspect the model folder for its content. Please note that this file browser is an open source third-party implementation. This is the example to show we can easily integrate a third-party implementation without modifying its code. At the end, we have the platform's pipeline execution engine where the endpoint is hosted. Once an infrastructure is defined as a graph, another MLOps engineer can deploy it either in the UI or through a simple command line as being shown here. Again, once the infrastructure is deployed, the MLOps engineer can open it in the platform UI. As you can see, for each block here, it has a status icon. Clicking on the icon will launch a dashboard for more detailed monitoring. Once all the status icons turn green, the infrastructure is up and running. For anyone Here is the view of the file browser content. The base model is the version used by the deployed pipeline originally. Even though after an infrastructure is deployed, the MLOps engineer can modify it and redeploy it through the UI. For example, he can actually drag in a TensorBoard component to monitor the retraining progress. The infrastructure definition can be exported in the YAML format. This YAML file on the right is exactly the one we use to deploy the infrastructure at the beginning. Now everyone can trigger the retraining and updating process by uploading a dataset to the data loader endpoint. It can be a human agent or software agent. The uploading will trigger the model update process. Eventually, the retrainer block will generate a new version of the model trained with this new dataset. The deployed pipeline service will detect its existence and use the model to update its existing model. This screen shows the retrainer has completed its training. Please note that the retraining process is further accelerated by Petuum Platform. We have observed a factor of 3 speed up, so that the training time has been reduced from several days to within a day. Now the model in the pipeline, the deployed pipeline, has been updated. Sending the same request again to the endpoint will use the new model for the translation. As you can see, the model version has been updated to version 5 instead of the base model. This is the end of my demo presentation. I think the key takeaway is that Petuum Platform supports composability and reusability from data application to infrastructure level, resulting in great productivity gain, covering the entire life cycle of AI application development, from local development to operationalization to MLOps process automation. Thank you, everyone. This is the end of the demo session.
Many thanks, Tong. We are really grateful to have you today. It was a pleasure hosting you. We are also grateful to our audience. Please join our Q&A channel and feel free to leave us any feedback about the session or ask any question. Our speaker will stay a bit longer and answer your question if you have any. Thanks again for joining us today. Thanks for the speaker for an amazing presentation. It was a pleasure having you today all. Enjoy the rest of ODSC conference and do not forget to take our short survey at the end of the session. It will help us shape future conferences. Thank you all. Oh, are you still here, Tong? Or
I'm still here. And what we should do? We should quit this webinar.
One question currently: is there a repo for this tool that you were presenting?
I'm sorry. Could you say it again?
Yeah, we have one question from attendee. Is there a repo for this tool?
Is there an application for this tool?
Repository for this tool. Is there
Oh, repository. Oh, okay.
Yeah.
Oh, okay. I got it. Yes, there are multiple repositories we use to construct the Petuum Platform product. At this moment, you need to sign up for the private beta trial to be able to access the product we just demoed here. The repos are not accessible publicly.